This event is more complicated than the other ones we've looked at. I've already applied a threshold of 5 GeV to the transverse momenta, so we don't have too many tracks to confuse things in the central detector. We can see that there are 4 muons in this event though, 2 of them going out this way and 2 of them going out that way. We can tell they're muons because they go all the way out through the layers of the detector to the muon chambers on the outside. Looking at the side view, we can see that actually one of them is going out through the central pass of the muon chambers, and the other 3 are going more longitudinally towards these end cap muon chambers. We want to mark these all as muons, positive or negative. So let's use the finger select icon and select one of them and mark it as a muon. Then let's try selecting the next one that's quite close to it and marking that as a muon as well. Before we go any further, let's just look in the invariant mass window, and you can see we've got a kind of warning red incompatible notice here. Why are these incompatible? Well, we're looking for particles like Z, which is a neutral particle, so when it decays into, say, a positive muon, it must have a negative muon to match that charge. But here we've tried to combine 2 positive muons, 2 mu plus particles, and they couldn't possibly have come from a neutral Z boson. So let's get rid of one of these tracks, the second one. You just click delete, select it in this table, then select delete track. It doesn't actually delete the track from the event, just from the invariant mass window. Now we've still got our select icon. Let's have a look at these other 2 muon tracks on the left. Select one and look at the track momenta. This one is negative. The other one on the left is negative as well. So that's good news. We've got 2 positive and 2 negative. So we need to combine this positive muon we found with one of the negative ones. Well, let's just choose the top one for now and mark that as a muon. So this time we've got a positive and a negative, so they are compatible, and their invariant mass is just over 88 GeV. So that means if they did come from a neutral particle, that neutral particle had a mass of about 88 GeV, which is pretty close to the Z mass. As we've discussed, we don't always expect to get exactly the same value. Now, I could equally well have combined that particle, the positive muon, with this negative muon, and then we'd have 2 different pairs with 2 different invariant masses. If we were doing a real physics analysis in Atlas, we would have to have a rigorously defined algorithm for deciding which pairs to match together. For today, we're not going to worry too much about that. So we've already got one pair. We know that the other ones will also have compatible masses. So let's select this one, mark it as a muon, select the last one that we haven't counted yet, mark that as a muon, and then look back at our invariant mass window. So we've got 2 pairs, one of which has got a mass of about 88 and one of about 94. So they're both reasonably close to the Z mass, although not dead on. We've also got another number here. So this column, 193 GeV, this is the invariant mass of all 4 muon tracks put together. So if we had a neutral particle that had decayed into 4 muons, this is the invariant mass it would have. When the Higgs boson was discovered, it was partly using events like this that we were able to find out that it existed and what its mass was. In fact, the mass turns out to be about 125 GeV, so this is a background event. It's not actually from a Higgs boson, but we had to plot many events with different masses in a histogram to actually find the evidence for a peak at 125 GeV.